So today we're talking about multiplying and dividing rational numbers, and our Common Core standard is NS 7.1D, applying properties of operations as strategies to add and subtract rational numbers. Now, rational numbers are just a fancy way of saying numbers that can be written as a fraction. So you may want to include that in your notes. A rational number can be written as P over Q, or as a fraction. That does also mean that whole numbers can be rational numbers, correct? Because let's say, for example, I had 4 ones, that would equal 4, but that is also a rational number. Rational numbers also include the number 0, because I could have 0 halves, which would equal 0. So rational numbers will include all fractions, whole numbers, and the number 0. Today we're going to focus mostly on fractions. So once you have your template secured in your notebook, we're going to open up all of our flaps so that we can only view the examples on the inside. The first example we're going to start with is multiplying rationals, just multiplying a simple rational number. So multiplying and the method for multiplying a rational number is quite straightforward. It asks you to multiply the numerators together in addition to multiplying the denominators together. So you multiply 3 times 6 would equal 18 over 4 times 15 would equal 60. Of course, as always with fractions, we always want to make sure we simplify our answers at the end. So 18/60ths have a common factor so far of 6. So 18 divided by 6 is 3, 60 divided by 6 is 10, and my final answer is 3/10. Dividing rational numbers is similar. However, we are going to use a method which I like to call the bouncing ball method. And hopefully you'll see why I call it that. If I have the numbers 3/8 and I'm dividing by 9/12, I imagine that I have this ball that I'm going to bounce through the problem in order to solve. When I bounce the number through the problem, it creates this line, and then it goes back up. So whatever I bounce through should be in my numerator. And then I'm going to bounce my blue ball from the bottom up and then back down to the bottom. So my blue bounce should end up in my denominator and my red bounce should end up in my numerator. When I bounce those two numbers, in the middle I get this great X cross, and that is going to change to multiplication. So instead of having a division symbol, I'm going to bounce my ball through the problem. The red ball is going to go from right here through the multiplication. So 3 times 12 is going to equal and end up at my solution. 3 times 12 is 36. Now I'm going to do the same with my blue ball. Start at the 8, bounce it upwards. 8 times 9 is going to equal 72. So my answer here is 36 over 72. And now all I have to do is simplify. So I can decide what common factors there are. The first one that jumps out at me is 2. So 2 divided by 36 is going to be 18. And then 72 divided by 2 is going to be 36. So that helps us out a little bit because I have that 36 in common with the numerator. So instead, I'm going to say 36 over 72 divided by 36 36ths to get my final answer of 1/2. Again, I use the bouncing ball method, which tells me if I have A over B divided by C over D, I'm going to multiply A times D over B times C. Let's move on to still a rational number, but it's a mixed number. A mixed number shows us that they have a whole value in addition to the rational number. The most important thing with mixed numbers is rewriting them as irrational fractions. So at any time we're using mixed numbers, we want to be sure to rewrite as an irrational fraction. And what that means is that my numerator is larger than my denominator. And now that's key because it seems a little silly, but that's what we're looking for. So in this first example, I have 5 as my denominator, but I have a mixed number, so there's a whole value of 2. So what I need to know is how many fifths would exist in 2 wholes. In order to do that, I say 5 times 2 equals 10. So now I have 10 fifths in addition to the 4 fifths that are already assigned to that fraction. So my new value is going to be 14 fifths. I do the same thing to the other side of the equation in that my 7 in the denominator is going to be multiplied by 3 wholes to see how many sevenths exist in 3 wholes. In this case, it's 21. Then I'm going to add the existing sevenths from my numerator. So 21 plus 4 equals 25 sevenths. Then I'm going to continue to just multiply as usual. 14 times 25 over 5 times 7. Go ahead and complete that problem in your notes for me and see if you get the right answer. Lastly, we are going to change those mixed numbers into irrational numbers in our final division problem. And again, we follow that method of multiplying the denominator times the whole number to find the value, and then adding the existing numerator. So my problem says 14 over 3 divided by, again, 9 times 2 plus 4 would be 22 over 9. Solve the division just the way we would if it was a traditional division problem for rational numbers. And go ahead and do that on your own as well. Finally, you'll have several proof problems here to do on your own. Please select 2, one mixed number problem and one regular rational number operation to solve. You do not have to do all 4. You can do 2 problems. If you'd like, you may also do all 4. However, it's not necessary.